Let's look at another example of circular motion when we're going around a bank curve. Now, you might have seen bank curves in, say, cycling, those velodromes, very steeply banked. But bank curves are everywhere. Every curve is subtly banked. It might be a very, very small angle on some of them. But on the roads, those curves are all slightly banked. So the green there represents the bank, and the red is the object going around it, if you like. So we've done a cross-section. The forces that have come into play. As I mentioned the other day, whenever an object makes contact with a surface, there will be a normal force at right angles to the surface. So we have that force. Gravity still comes into play. That's about it. What ends up happening, it actually turns out to be very similar to the conical pendulum. Because the conical pendulum simply had gravity and then tension going in at an angle. So when we start resolving these forces, we see very similar equations. So horizontally, it's just moving in a circle. So they would sum to give mv squared on r. And horizontally. But in order to resolve my normal forces, I need to know where theta is going to be in the right angle triangle. So again, we can play with geometry, and this angle here would end up being theta, because we know that that's at right angles, and we can draw in a parallel line in there if we wanted to, and we could prove that was theta. So, all right, so the component horizontally becomes n sine theta. And that's the only horizontal force we have, so n sine theta will equal our resultant force of mv squared on r. Vertically, again, nothing's happening, at least we hope nothing's happening. When we're going around the corner, we don't all of a sudden want the car to jump up in the air. And so we have a vertical component, n cos theta, and gravity as well. So like I said, we end up with very similar equations. Just I've got n there instead of the letter t. And so again, we can do similar things to what we did with the conical pendulum. I could eliminate the normal force and come up with this expression. Tan theta is v squared on rg, and so on. So okay, let's have a look at a question. We're going to have a railway line that can go around. Now, if we're in a train, of course, it's very important we stay on the tracks. So we need to know the speed that we can go around without the train lifting, if you like, off the tracks. So we've got our information. The radius of the curve is 400 metres. Distance between the rails is 1.5 metres. And as I say, it's a very slight bank. The outside rail is 0.8 of a metre above the inside rail. So we want to find the best speed that will stop it moving up. So that's the representing the outside wheel, if you like. So I know the distance between the wheels, 1.5 metres, and the height, 0.08, we said. So there's Bob, the normal force, gravitational force, and again, we'll work out theta so we can get our components of the normal force. All right, so like I just did, horizontal forces will sum to be mv squared on r. We only have n sine theta as the only horizontal force. And vertically, we want it to be 0. We don't want our train to be moving up. So n cos theta and mg. And just like there it is. So tan theta is v squared on rg. Now I can work out tan theta because I now have some measurements of, well, sine theta is 4 on 75 if I work out opposite over hypotenuse. So if that's sine theta, I can then work out tan theta. Pythagoras will get me the other side. Turns out to be 4 on the square root of 5,609. So subbing that in for tan theta, we know the radius, we know gravity, we want to find the velocity to go around this corner. And so 14.47 metres per second when we calculate that one out, or 52 kilometres per hour would make more sense, I suppose, if we're driving our train. Let's look at an HSC question, so from a while ago now, but it's adding in yet another force. And there is another force that happens, which is called friction. Okay? Right? That's why when we're travelling with constant velocity in a horizontal direction, we do actually end up stopping, because there is another force happening there, and that is friction. and the friction is slowing you down. So friction is always in the opposite direction to which we're travelling. It's a resistive force. So they set up our question for us. Particle mass m going around the circular track, radius r. There's our centre over here, c. They've told us the angle of the bank is theta, and our particle is not moving up or down. So we have the reaction force, which is n there, component of friction directed up or down. Now it depends, because it depends what the particle wants to do. If the particle wants to move up, then friction would be going down the bank. But if the particle wants to go down the bank, then friction would be going up the bank. So that's why it could be either up or down. In their diagram, they've placed it up. And it lies in the range minus mu n to mu n. Friction always turns out to be some multiple, some constant of the normal force. And mu is a positive constant. The sign of F, they've defined positive to be up the bank. So it'll be positive mu n when it's going up the bank. Acceleration due to gravity is g, and they've also given us the circular motion acceleration of v squared on r, and that's directed towards the centre. All right, so what's the actual question? By resolving forces horizontally and vertically, show this wonderful looking expression there. Okay? Well, it all starts the same. Let's resolve them, but I'm going to need a component for both the frictional force and the normal force, because it's neither horizontal or vertical. So I need to work out where theta is. Well, once again, theta turns out to be in that position for the normal force. But if that's a right angle, then for the friction triangle, theta would be up the top there. We can work out. So horizontally, mv squared on r, we will now have a component going to the left for the normal force, component going to the right for the frictional force. The frictional force would be negative, because remember the resultant force is going towards the centre of the circle. So the centre of the circle is positive that direction. Okay, let's do the vertical ones. So again, we have our normal force, but we also have a component of frictional force and also gravity as well. And so they would sum together to give 0. Now, let's try and construct the expression. They've got n sine theta minus f cos theta. Well, that actually is what we've got in the horizontal forces. And the vertical forces, actually, it's quite an easy little problem. So when you first look at it, you think, oh my God, how am I going to get that? But if you do your force diagrams up, it turns out, oh, quite simple, really. Don't know why I did it the long way round. But anyway, here we go. I've said v squared on rg is mv squared on r times 1 on mg, and then subbed in. It's sort of reverse logic to what I probably should do, because we can just substrate it and get it. But anyway, however we show it, there it is. V squared on rg is that wonderful expression. Now, we want to find the maximum speed, or they've told us what it is. We want us to confirm it, that we can travel without actually slipping up the track. And we can suppose that mu tan theta is less than 1. Now, it's friction that's stopping it moving it up or down. And it's saying without slipping up the track. So therefore, friction in this problem is actually going down the track. And so in this case, friction is minus mu n, not positive mu n. Because remember, they defined positive to be going up the track. So that's the only difference. Well, we just worked out v squared on rg. All I'm going to do is, instead of using mu n for f, I'm going to use minus mu n. And if I sub that into what we just worked out, that's what we get. N sine theta plus mu n cos theta on n cos theta minus mu n sine theta. Now we have to work out which one of less velocity. Okay, n clearly divides. It's in everything. I'm looking at the answer I'm trying to get. It's got tan thetas in it. I've only got sines and coses. How do I turn that into tan? Well, divide by cos. Sine divided by cos is tan. So I'm going to divide everything by cos. And so sine on cos becomes tan, cos on cos becomes 1, and then on the bottom, cos on cos is 1, sine on cos is tan, and we've got the expression that they were we're looking for. So really, all that was involved in this question was substituting in for F, but realising it was minus mu n we were substituting in, not positive mu n. Now, if mu is greater than or equal to tan theta, the particle will not slide down the track regardless of its speed. This is what we now have to prove. So now I'm looking for the minimum speed. That was the maximum speed we could travel. Minimum speed, but friction now will be positive mu n because we're sliding down. We want to stop sliding down, so friction will be acting up. So we just proved when friction was minus mu n, we got tan theta plus mu on 1 minus mu tan theta. The only difference with this problem is friction now is positive mu n. So that would change my eventual answer to be tan theta minus mu on 1 plus mu tan theta. I don't have to go and derive the whole thing again. Because the only difference is I'm substituting in positive mu n instead of negative mu n. They've told me that mu is greater than or equal to tan theta. Well, that means the top of the fraction, what's going to happen to that? Yeah, it's got to be a negative number, doesn't it? Because if mu is bigger than tan theta, well, tan theta minus something that's bigger than it, got to be negative. But remember that point they made before, that we could suppose that mu tan theta was less than 1. So, well, we're adding anyway. So the bottom's going to be positive. So therefore, I know v squared on Rg is going to be less than or equal to 0. But R and G are just constants. So that means v squared is less than or equal to 0. But v squared can't be negative. So therefore, the minimum speed that I can travel is 0. Well, that means I can go any speed. And that's what the question is asking us to prove. Show that it will not slide down regardless of its speed. Okay? So the minimum velocity it can travel without sliding down is 0. Therefore, it's never going to slide down. Doesn't matter what speed I'm travelling. Here's an interesting question. It's not a bank curve, but I liked it. I thought we'd have a look at this one. It's also still got to resolve forces. We've got a circular drum, and inside our circular drum is a little ball bearing or something. So a particle P is, well, they've called it particle, ball bearing or something, is rotating in the vertical circle without slipping on the inside of the drum. So as we go, the radius of the drum they've given us, the angular velocity we're turning the drum is omega radians per second. Acceleration due to gravity is its normal g. Mass of my ball bearing is m. Centre. So basically they're just setting up the question for us. They've also told us all the different forces. We know there's going to be a normal force. Now, here's the interesting thing with this problem. Remember, the particle is on the inside of the drum. And we said the normal force always acts at right angles to the surface. Well, when we're talking about a circle, at any instant, we think of the surface to be the tangent. And at right angles to the tangent is the radius. So the normal force, therefore, acts along the radius. So the normal force in this problem goes towards the centre. So that's why they've drawn it that way. And there will be a frictional force. It will go along the surface. Well, again, the surface at an instant would be a tangent, and so that's why our frictional force is going off at a tangent at the point. By resolving forces perpendicular and parallel to OP, find expression for F over N. You see, we don't always have to resolve horizontally and vertically, as long as our two components are perpendicular to each other. So it can be useful because the normal force and the frictional force will always be at right angles to each other. So sometimes we'll resolve in the direction of those forces, and then I don't need to know one to do the other. And so that's what they're asking me to do. So I can get my head around it, because I'm so used to doing horizontal and vertical, I've turned the problem to make it look like, okay, the frictional force is now horizontal and the normal force is now vertical. It means now gravity is no longer going down. It's going off at an angle. So I'm going to have a component of gravity. well, actually, there's my components of gravity. Okay. Well, okay. So forces perpendicular to OP will be equal to 0. There it is. So for F and mg cos theta. So no mention of n at all. So I now know mg cos theta minus F is equal to 0. So F is mg cos theta. Forces parallel to OP, see, it's no longer a horizontal force, because remember, it's going towards the centre. I've now turned it into what looks like a vertical force. And so the forces parallel to OP will be mr omega squared. And so let's draw those in. Now the normal force, but then a component of gravity. So they were summed together to give mr omega squared. Okay, so F divided by N, I just simply substitute in what I've just found and we come up with a result. F over N is G cos theta on R omega squared minus G sine theta. I could have done that with the bank curve question as well. Watch what happens. Here's my bank curve in its traditional position, and I would have had the normal force going up, gravitational force going down, friction going whichever. I've got it pointing down for this one. But I could have rotated the problem so the frictional force looks like it's horizontal and the normal force looks like it's vertical. So once again, I'm going to get a component of gravity in this problem. But here's the interesting one for this one, the resultant force. The resultant force is neither horizontal or vertical because it's going towards the centre. Right? So where it was in the original one horizontal, I've rotated the problem. It's now going off at the angle. So there will actually be a component of that resultant force in both directions. So I'll need to know where theta is in that triangle. Okay, so forces along the bank, the resultant force along the bank, which is the one I've now looks like it's horizontal, would be mv squared on r cos theta. And drawing all the ones that look horizontal in my picture, I've got friction going to the left and a component of gravity going to the left. And so F plus mg sine theta is mv squared on r cos theta. And that allows me to find the frictional force without having to worry about the normal force. And similarly, I could go along the bank, perpendicular to the bank. Its component would be mv squared on r sine theta. And I've got the normal force going up, component of gravity going down, and they would add together to give mv squared on r sine theta. And I've now got an expression for the normal force without having to worry about the frictional force. So it's an alternative way of resolving forces, going in the direction of the normal and the frictional force instead of going horizontal and vertical. Okay. So, couple out of the Cambridge, couple out of the Patel. There we go.